February 20th, 2026 is already written in Earth's electromagnetic memory, and the dominoes started falling weeks ago. Right now, while you're listening to this, our planet is moving through conditions it hasn't experienced in recorded history. Solar radiation at 20-year peaks, earthquake clusters that defy their own statistics, the electromagnetic heartbeat between Earth's surface and sky pulsing in rhythms it shouldn't. And somewhere, 24,000 light-years away, a signal arrived at precisely the wrong moment to be coincidence. This isn't astrology. This isn't prophecy. This is pattern recognition at the edge of what our instruments can detect. Stay with me until the end, because what's approaching isn't just an alignment. It's a threshold, and we're about to discover whether Earth is responding to something or becoming something. Subscribe and follow along, because as these dominoes continue falling through February, what emerges will show us whether we truly comprehend how Earth's electromagnetic and geophysical systems communicate, or whether there's a hidden layer of coupling we've never mapped. Invisible threads connecting solar physics to seismic behavior to atmospheric electricity that have always been there, waiting for us to build machines capable of seeing them. Something began moving months before anyone realized the clock had started. February 20th, 2026 is not when this story begins. February 20th is when everything that's been quietly shifting beneath the surface of our electromagnetic reality finally reaches critical mass. The planetary alignment everyone keeps talking about isn't the match that lights the fuse. It's the moment the fuse runs out. You've probably heard the warnings already. 7 planets arranged in a line across our sky. Saturn and Neptune locked in their once-in-a-lifetime dance. The kind of celestial geometry that gets astrologers excited and scientists dismissive. And for good reason, usually. Planetary alignments happen with predictable regularity. Gravitational effects are measurable and negligible. The distance involved means that even when planets appear to line up from our perspective, they're still separated by incomprehensible gulfs of space. So why would this time be different? Because the dominoes started falling in January. Right now, in late January 2026, our sun is behaving strangely. Not catastrophically. Not apocalyptically. Just strangely. The kind of strange that makes solar physicists tilt their heads and quietly double-check their instruments. We're seeing solar activity that doesn't quite follow the script we've written for solar cycle 25. Radiation storms that linger when they should dissipate. Geomagnetic conditions that pulse with a rhythm nobody predicted. At the same time, seismographs across the globe are recording earthquake patterns that violate their own statistical logic. Magnitude 5 events clustering in ways that shouldn't happen without larger triggers. The Earth's crust is redistributing stress without releasing it the way we expect. Something is loading the system instead of unloading it. And then there are the Schumann resonances. For 72 consecutive hours in January, the electromagnetic heartbeat of our planet went haywire. Not louder, not quieter, just different. The standing waves that normally hum along at predictable frequencies started doing something nobody had seen sustained for that long. Northern monitoring stations lit up with signals that looked less like natural variation and more like someone was turning a dial. Here's where it gets uncomfortable. These things don't usually happen together. Solar physics operates on one timescale, seismic systems on another, atmospheric electromagnetism on a third. They're coupled, yes, but loosely. They influence each other the way distant cousins might acknowledge each other at a family reunion. Polite nods, minimal interaction. But in January 2026, they started moving in sync. This is what scientists call multi-domain synchronization, when separate systems that normally operate independently begin coordinating their behavior. When patterns emerge across disciplines that have no obvious reason to be talking to each other. It's the difference between three metronomes ticking at their own pace and three metronomes that suddenly lock into the same rhythm despite being in separate rooms. And synchronized anomalies matter more than extreme single events. A massive solar flare is impressive, but predictable. A major earthquake is tragic, but statistically expected somewhere on Earth every few weeks. An electromagnetic disturbance can be explained by local conditions. But when all three happen in a coordinated sequence, when the timing starts to feel less like coincidence and more like choreography, that's when the questions change. Think of it like this. Imagine you're watching dominoes fall, but you can't see the whole chain. You see one tile tip over here, another falls there, a third goes down across the room. Individually, they could be unrelated. Someone bumped a table. A breeze caught one. Pure chance. But if they're all falling in sequence, moving toward some invisible point of convergence, then you start looking for the hand that pushed the first one. The cosmic domino effect isn't about any single system going critical. It's about the spaces between systems starting to close. Solar radiation doesn't just hit Earth and bounce off. It couples with our magnetosphere. That coupling affects ionospheric conductivity. Ionospheric changes alter the global electric circuit. The global electric circuit influences atmospheric pressure systems. Atmospheric pressure affects seismic stress at fault boundaries. Each system nudges the next. No smoking gun. Just a cascade of whispers building towards something louder. And here's what keeps researchers up at night. We don't have good models for this. Our understanding of each system individually is pretty solid. Solar physics has come a long way. Seismology has sophisticated monitoring networks. Atmospheric science can track electromagnetic changes with precision. But the interfaces between these systems, the moments where solar becomes seismic, becomes electromagnetic, those transition zones are still partially mapped territory. We know they exist. We don't fully understand how they work under stress. So when multiple systems start showing anomalies simultaneously, we're forced to ask questions we usually don't need to ask. Is this correlation or causation? Are these systems responding to the same external input, or are they actually driving each other? And perhaps most unsettling, is there a variable we haven't identified yet? Something already inside the timeline that we simply haven't noticed because we weren't looking in the right place? Let me introduce you to something called 3I/Atlas. It's an object currently moving through our solar system. An interstellar visitor, potentially, though confirmation is still pending. Right now, it's heading toward Jupiter. Right now, Earth's orbit is carrying us through the space it already passed through. And right now, nobody's quite sure what that means. Because here's the thing about interstellar objects. They don't travel alone. They bring their own neighborhood with them. Dusty plasma clouds, magnetic field structures, debris that can extend for millions of miles behind the visible object itself. And if Earth is moving through that debris field right now, in January 2026, then we might be experiencing something our instruments weren't designed to detect. A slow electromagnetic drift, a subtle shift in the baseline conditions of near-Earth space. Not dramatic, not dangerous, just different enough to matter. This is what makes February 20th so compelling as an endpoint. It's not that the alignment itself generates enormous forces. It's that the alignment represents maximum geometric convergence at the exact moment when Earth has been marinating in unusual conditions for weeks. Multiple systems already stressed. Multiple baselines already shifted. And then the planets arrange themselves in a configuration that amplifies whatever subtle coupling effects are already in play. The investigation ahead isn't about prophecy. It's not about certainty or prediction or claiming to know what will happen. It's about pattern recognition under uncertainty. It's about looking at data that doesn't quite fit and asking whether the models are wrong or whether something genuinely new is occurring. It's about taking seriously the possibility that February 20th isn't when something starts. It's when something completes. So if February is the endpoint, if that alignment is the moment when invisible processes become visible, when synchronized anomalies reach some threshold of coordinated behavior, then the real question isn't what happens on that day. The real question is, what set the first domino in motion? What pushed the system out of equilibrium weeks or months ago? What started this cascade before anyone knew to look? And to answer that, we need to go back to where the signals first appeared. January 2026 began with the sun reminding us who's in charge. On January 6th, an X-class solar flare erupted from the sun's surface with the kind of energy release that makes space weather forecasters sit up straight. X-class flares are the heavyweight champions of solar activity. They represent the top tier of electromagnetic fury our star can throw at us. This particular flare triggered an S4 radiation storm, the second highest category on the scale, and sent a wave of charged particles screaming toward Earth at millions of miles per hour. Within hours, our planet's magnetosphere was experiencing G4 and G5 geomagnetic storm conditions. That's the top two categories. The kind of activity that knocks out radio communications at high latitudes, scrambles GPS signals, and sends auroras dancing across skies where they're rarely seen. Operators of satellites and power grids go into high alert mode. Aurora photographers grab their cameras and head north. It's dramatic. It's powerful. And it's exactly the kind of event we've seen before, during active solar cycles. Except this time, something was off. To understand why, you need to know that there are actually two different kinds of storms happening when the sun decides to get violent. First, there's the radiation storm. That's the high-energy particles, mostly protons, that arrive first because they're traveling near the speed of light. They can reach Earth in minutes. They're dangerous to astronauts and satellites, but our atmosphere shields us at ground level. Think of it like getting hit by a flashlight beam. Dangerous if you're in space, barely noticeable if you're protected. Then comes the geomagnetic storm. That's when the slower-moving solar wind arrives, carrying with it the twisted magnetic fields from the eruption site. This can take anywhere from 1 to 3 days. When that magnetized solar wind slams into Earth's magnetic field, it's like two opposing magnets colliding. Energy transfers. Currents flow. The whole magnetosphere rings like a bell. This is what causes the auroras, the satellite glitches, the power grid fluctuations. We're used to this two-stage process. Radiation storm first, geomagnetic storm second. Quick punch followed by a prolonged shove. What made January different was how long that shove lasted and how it was oriented. Solar wind carries with it something called the Interplanetary Magnetic Field, or IMF. That field has an orientation, a direction it's pointing, and that direction matters enormously for how effectively it can couple with Earth's magnetic field. Scientists measure this using a coordinate system where the Z component, called BZ, tells you whether the field is pointing north or south relative to Earth's magnetic poles. When BZ points south, bad things happen. Southward IMF allows the solar wind to couple efficiently with Earth's magnetosphere through a process called magnetic reconnection. Energy pours in. Storms intensify. This is the configuration that drives the biggest geomagnetic disturbances. When BZ points north, the coupling is much weaker. Northward IMF tends to slide around Earth's magnetic field rather than penetrating it. Storms fizzle, energy transfer drops. This is the configuration forecasters hope for after a big solar eruption. In January, the BZ component was predominantly positive. Northward, the solar wind should have been mostly deflected. The geomagnetic storm should have been modest, maybe G2 or G3 at most, and it should have ended quickly once the main pulse passed. Instead, we got G4 and G5 conditions that persisted for an unusually long time. Not because the wind was hitting harder, but because something about the coupling mechanism was more efficient than normal. The electromagnetic connection between the Sun and Earth wasn't behaving the way the textbook said it should. This is where things get speculative, but it's educated speculation grounded in data. What if the issue isn't the strength of the connection, but the duration? Standard models of geomagnetic storms focus on peak intensity. How hard did it hit? How much energy transferred in the critical moments of reconnection? But those models are less sophisticated when it comes to sustained, low-level coupling over extended periods. Think of it like this. You can heat a pot of water with a blowtorch for 30 seconds, or you can heat it with a candle for 30 minutes. The blowtorch is more dramatic, but the candle might actually raise the water temperature more overall because the energy keeps flowing. January's solar wind was the candle. Not as intense as it could have been, but it stayed connected longer than normal. It lingered. And lingering matters when you're talking about coupled electromagnetic systems. Earth's magnetosphere isn't a static shield. It's a dynamic structure with resonances and feedback loops. The ionosphere, the layer of charged particles high in our atmosphere, responds to sustained driving in ways that brief pulses don't trigger. Radiation belts, those zones of trapped particles surrounding Earth, can be pumped up by persistent energy input, even if each individual pulse is weak. There's also something called the global electric circuit, a phenomenon where electrical potential differences exist between the Earth's surface and the ionosphere, maintained by thunderstorms and cosmic rays. This circuit is influenced by solar activity, but again, most research focuses on acute events. What happens during a slow, sustained perturbation? What happens when the driving conditions don't spike and drop, but instead elevate and plateau? Current models struggle with this, not because the physics is unknown, but because the computational complexity explodes when you try to track all the coupled effects over days instead of hours. Low-frequency coupling, the slow oscillations and drifts that occur when two systems stay locked together for a long time, is harder to model than high-frequency impacts. It's like the difference between predicting where a bouncing ball will land versus predicting how cream will swirl in coffee. One is simple mechanics. The other is fluid dynamics with 1,000 interacting variables. So here's the hypothesis, clearly speculative but grounded in observation. What if Earth's electromagnetic systems weren't being damaged in January? What if they were being retuned? What if that sustained, positive BZ solar wind was doing something more subtle than just transferring energy? What if it was shifting the baseline operating state of the magnetosphere-ionosphere system? Imagine a guitar string. You can pluck it hard and get a loud note that fades quickly. Or you can use a bow and sustain the vibration, and if you do it right, you can shift which harmonics are emphasized. The string is still vibrating. It's still the same fundamental frequency, but the overtones change. The timbre shifts. An expert could tell something's different, even if they couldn't immediately explain why. Earth in January might have been that guitar string, still vibrating at its normal fundamental frequencies, still operating within normal ranges for most parameters, but with something subtly different in the harmonic structure of its electromagnetic behavior. And if that shift occurred, if the baseline got quietly redefined by weeks of unusual solar wind coupling, then Earth heading into February 20th wouldn't be the same Earth that existed in December. The solar signal that didn't behave like a normal storm might not have been abnormal at all. It might have been doing exactly what it was supposed to do, delivering exactly the kind of influence it was designed to deliver, if design is even the right word for something emerging from the chaos of stellar physics. But the sun wasn't the only thing talking to Earth in January. Earthquakes follow rules. Not the kind of rules you can use to predict exactly when and where the next big one will hit, but statistical rules, patterns that emerge when you look at thousands of events over decades. Magnitude and frequency have a relationship. For every jump in magnitude, you expect about 10 times fewer earthquakes. Magnitude 4s are common. Magnitude 5s are less common. Magnitude 6s are rare. Magnitude 7s are headline news. Magnitude 8s reshape coastlines and rewrite history. January 2026 threw those rules in a blender. Between the 1st and 15th of January, seismographs recorded an unusual cluster of magnitude 5.0 to 5.9 earthquakes scattered across multiple tectonic regions. Chile, Indonesia, Alaska, Japan, Turkey. These weren't aftershocks from a massive main event. These weren't obviously related to each other geographically. What made them strange wasn't their individual magnitudes, it was their collective behavior and the conspicuous absence of what should have come next. In normal earthquake statistics, when you see a cluster of 5s, you expect at least a few 6s. The distribution is predictable, but January's cluster stopped at 5.9. Multiple events right up against the threshold, and then nothing above it. No magnitude 6 or larger events during the same period. Statistically, that's like flipping a coin 20 times and getting heads 15 times in a row. Possible, but uncomfortable. Seismologists use something called the Gutenberg-Richter law to describe earthquake frequency magnitude distribution. It's one of the most robust statistical relationships in all of geophysics. It says that for a given region, over a given time period, the number of earthquakes decreases exponentially with magnitude. The math is elegant, and the fit to real-world data is remarkably consistent across different fault systems and tectonic settings. January's cluster didn't violate the Gutenberg-Richter law outright, but it sat at the edge of expected variation. And what made seismologists nervous wasn't just the cluster itself, but what it implied about stress distribution in the crust. Earthquakes happen when stress exceeds the strength of rock along a fault. Stress builds up slowly as tectonic plates grind against each other, and then releases suddenly when friction can't hold anymore. That release typically follows a cascade pattern. Small ruptures trigger slightly larger ones. Those trigger even larger ones. Eventually, you get a main shock that releases most of the accumulated strain, followed by aftershocks as the crust adjusts to its new configuration. But cascades can also work in reverse. Instead of stress being released through rupture, it can be redistributed without rupture. Imagine squeezing a water balloon. If you squeeze one end, the water doesn't disappear, it moves to the other end. The balloon is now under more stress at the new location, but it hasn't popped. Tectonic stress works similarly. A small earthquake in one location can shift stress to adjacent fault segments, loading them up without breaking them. What appeared to be happening in January was stress redistribution on a global scale, without corresponding stress release, through large ruptures. The 5s were real earthquakes, real energy releases, but they were too uniform in magnitude and too widespread geographically to fit standard aftershock or cascade models. It was as if the Earth's crust was adjusting to something, shifting weight from one foot to the other, finding a new balance point. There are only a few mechanisms that can cause this kind of distributed stress change. Slow slip events, where faults creep without generating seismic waves, can do it. Fluid pressure changes deep in the crust can do it. Thermal expansion from magma intrusion can do it. But all of those mechanisms tend to be localized. You see the effects in one region, not globally. So what kind of input produces earthquakes distributed across multiple tectonic plates, all hovering around magnitude 5, all stopping before the threshold of major damage? The uncomfortable answer is that we don't really know. Not because the physics is mysterious, but because we rarely see this pattern clearly enough to study it. Earthquake catalogs are noisy. Magnitude uncertainties are real. Declaring a cluster statistically significant requires careful analysis to avoid seeing patterns in random noise. But when you combine the seismic data with everything else happening in January, the solar anomalies, the electromagnetic disturbances, the pattern starts to feel less like noise and more like signal. There's a known but poorly understood connection between electromagnetic phenomena and seismic activity. It's called seismo-electromagnetic coupling, and it's been documented for decades despite remaining controversial. Before major earthquakes, some monitoring stations detect unusual electromagnetic signals, radio frequency emissions, changes in ground electrical potential, variations in the ionosphere directly above future epicenters. The mechanisms are debated. Some researchers think it's piezoelectric effects, where stress on crystalline rock generates electrical currents. Others point to radon gas release, or fluid movement creating charge separation. Still others suggest it's related to changes in the global electric circuit. What's not debated is that the signals sometimes appear. What is debated is whether they're predictive, coincidental, or artifacts of instrument sensitivity. But what if the causation runs the other way? What if electromagnetic changes in the ionosphere or magnetosphere can influence seismic stress distribution? Not directly causing earthquakes, but modulating the threshold conditions that determine when and where stress releases? This is deeply speculative territory, the kind of hypothesis that gets geophysicists raising eyebrows and demanding extraordinary evidence. The energy scales don't obviously match. Electromagnetic fields in the upper atmosphere are diffuse and weak compared to tectonic forces. The coupling mechanisms would need to operate through intermediate steps, perhaps involving fluid dynamics in the crust or subtle changes in rock conductivity. But consider this. The Earth's interior is not electromagnetically inert. The mantle conducts electricity, poorly but measurably. The core generates Earth's magnetic field through dynamo action. There are feedback loops between thermal convection, magnetic field generation, and rotational dynamics. These systems operate on geological timescales normally, but they're not isolated from external inputs. If something were perturbing Earth's magnetic field from outside, not dramatically, but persistently, could that perturbation reach deep enough to affect stress distributions in the lithosphere? Could it alter the timing of when stress gets released versus redistributed? There's historical precedent for asking these questions, even if there aren't clear answers. During periods of intense geomagnetic storms in the past, some researchers noted temporal correlations with seismic activity. The correlations were weak and inconsistent, barely above statistical significance, but they were there. Most scientists attributed them to coincidence or selection bias. A few kept collecting data, waiting for better instruments and longer time series. January 2026 might be giving us that data. A period when electromagnetic forcing was strong enough and sustained enough to produce measurable effects, if such effects exist. A natural experiment running in real time across the planet. And if the seismic system was being loaded rather than released, if stress was being redistributed in preparation for something rather than relaxing after something, then the question becomes, what happens when the loading process completes? What happens on February 20th when the geometric configuration of the solar system reaches maximum coherence and whatever has been gently pushing on Earth's systems for weeks suddenly reaches its endpoint? The answer might be nothing. Statistical clusters happen. Electromagnetic anomalies happen. Coincidences happen, and sometimes they pile up in ways that look meaningful but aren't. But the alternative, the possibility that Earth's interconnected systems are responding to inputs we're only beginning to detect, is worth taking seriously. Because if it's real, if the dominoes are actually falling in sequence, then we're not just watching random events. We're watching a process unfold. And processes have endpoints. There's an electromagnetic heartbeat thrumming between the surface of the Earth and the bottom of the ionosphere right now. It's been there since before humans existed. It'll be there long after we're gone. Scientists call them Schumann resonances, named after Winfried Otto Schumann, who predicted their existence in 1952. They're standing electromagnetic waves that circle the globe, trapped in the cavity between Earth's conducting surface and the ionospheric plasma, roughly 60 miles overhead. Lightning strikes generate these waves. Every time lightning flashes somewhere on Earth, and that happens about 100 times per second globally, it pumps energy into this cavity. The cavity has preferred frequencies where waves fit perfectly, where they can circulate around the planet and reinforce themselves. The fundamental frequency is about 7.83 Hertz. That's 7.83 cycles per second. Higher harmonics exist at roughly 14 Hertz, 20 Hertz, and so on, but the fundamental is the strongest and most stable. 7.83 Hertz is not arbitrary. It's determined by the size of the Earth and the speed of light. Those two constants dictate the resonant frequency of the planet's electromagnetic cavity. It's as fundamental to Earth as its mass or its rotation rate. And in January 2026, for 72 consecutive hours, that stable, predictable electromagnetic heartbeat started doing something it's not supposed to do. Monitoring stations across the northern hemisphere recorded sustained disturbances in Schumann resonance patterns. Not brief spikes, not isolated anomalies. Sustained deviations lasting 3 full days. The fundamental frequency remained near 7.83 Hertz. That's fixed by physics, but the amplitude and shape of the resonance peaks changed. Multiple harmonics activated simultaneously. The normally smooth spectral signature got jagged and complex. Now, Schumann resonances do vary. They fluctuate with global lightning activity, which changes with weather patterns and seasons. They respond to solar activity, which can alter ionospheric conductivity. They show day-night variations as the ionosphere height changes. All of this is normal. But 72 hours of continuous complex behavior across multiple monitoring stations is not normal variation. It's something else. The first question is whether this was a real global phenomenon or an artifact of where we're measuring. Schumann resonance monitoring stations are not evenly distributed across the planet. Most are in the northern hemisphere because that's where most scientific infrastructure exists. So when northern hemisphere stations light up with anomalies, you have to ask whether this is telling you something about Earth or something about your instrument network. Southern hemisphere stations did show activity during the same period, but less intense. That asymmetry could be real, a genuine north-south difference in electromagnetic behavior, or it could be instrumental bias. More sensitive equipment in the north, better data processing, more careful monitoring. The honest answer is we don't know for certain, but the duration and consistency of the northern signals argues for something real. What makes the Schumann phenomenon particularly fascinating and controversial is the frequency overlap with human brain activity. Human brainwaves fall into several categories. Delta waves during deep sleep run from 1 to 4 Hertz. Theta waves during meditation or light sleep run from 4 to 8 Hertz. Alpha waves during relaxed wakefulness run from 8 to 13 Hertz. Beta waves during active thinking run higher. Notice where Schumann resonances sit. The fundamental at 7.83 Hertz falls right in the theta range. The first harmonic at 14 Hertz sits in the alpha range. This overlap has spawned decades of speculation about whether Schumann resonances influence human consciousness, whether they serve as a kind of planetary tuning fork that biological systems entrain to. The mainstream scientific position is clear and emphatic. Overlap does not equal causation. Just because two things share a frequency range doesn't mean one affects the other. Radio waves at 14 Hertz don't make your brain oscillate. At 14 Hertz, any more than hearing a musical note makes your skull vibrate at that pitch. Biological systems are far too complex and well shielded by tissue and fluid to be directly driven by weak external electromagnetic fields. But notice the careful language there. Directly driven. Mainstream science is confident that Schumann resonances don't control brainwaves like a remote control. What's less certain is whether they might influence biological rhythms indirectly, serving as weak environmental cues that biological systems incorporate, alongside light, temperature, and other cyclical inputs. This is where scientists tend to go quiet. Not because they believe in pseudoscience, but because the research is difficult and underfunded. Studying subtle long-term effects of environmental electromagnetic fields on biology requires huge sample sizes, careful control of confounding variables, and sophisticated statistical analysis. It's easier and more fundable to study acute effects of strong fields, the kind that power lines or MRI machines generate. So when January's Schumann anomaly occurred, when that 72-hour disturbance rippled through the electromagnetic cavity we all live inside, mainstream science wasn't prepared to say it affected anyone or anything. But a few researchers were paying attention, quietly taking notes, adding data to long-term data sets they've been maintaining for years. Because here's the deeper question underneath all the speculation about biological effects. Why were the Schumann resonances disturbed in the first place? What was driving that sustained, complex behavior? Lightning activity wasn't significantly unusual during that period. Solar activity was elevated, yes, but we've had comparable solar storms before without producing 3-day Schumann anomalies. Ionospheric conductivity, changes from solar radiation, don't typically generate the kind of multi-harmonic complexity that was observed. This raises the possibility that Earth's electromagnetic cavity wasn't just responding to internal drivers like lightning and solar input. Maybe it was responding to something else. Some external field or input that we don't routinely monitor because we didn't know we needed to. Think about what the Schumann resonance cavity actually is. It's the space between a conducting surface, the Earth, and a conducting plasma layer, the ionosphere. Any change in the properties of either boundary changes the cavity behavior. We understand how solar radiation affects the ionosphere. We understand how lightning pumps energy into the cavity. But what about changes in the electromagnetic structure of near-Earth space itself? If Earth were moving through a region where the background electromagnetic field had different properties, even subtly different, that could alter how the cavity resonates. The fundamental frequency would stay locked to Earth's size and the speed of light, those are constant. But the amplitude, the quality factor, the harmonic structure, all of those could shift if the boundary conditions changed. This isn't wild speculation. It's basic cavity resonator physics. Change the walls or the medium inside the cavity, and the resonance properties change. The question is whether near-Earth space has walls or mediums that could change. And the answer is yes. The magnetosphere isn't rigid. It's a dynamic boundary that expands and contracts with solar wind pressure. Plasma density in the ionosphere varies constantly. And if something were altering the baseline electromagnetic environment around Earth, something slow and persistent rather than fast and dramatic, those changes would propagate into the Schumann cavity behavior. January's 72-hour event might have been Earth responding to a new input, a signal we weren't looking for because we didn't know it existed. Or it might have been Earth generating a signal in response to accumulated stress in its coupled electromagnetic systems. The difference between response and generation, between being driven and resonating on your own, isn't always clear in complex systems. Either way, what happened in January was the Schumann resonance system spending 3 consecutive days in an unusual state. And whatever caused that state, it wasn't purely local to Earth, because at almost exactly the same time, a signal arrived from a binary star system 24,000 light-years away. And that timing, that coincidence, is where probability starts to break. Cygnus X3 is a monster. 24,000 light-years from Earth, buried in the plane of our galaxy, there's a star system that defies easy understanding. It's what astronomers call a high-mass X-ray binary. That means you've got 2 objects locked in a tight orbit. One is almost certainly a massive star, probably a Wolf-Rayet star shedding its outer layers at an insane rate. The other is compact, dense, a neutron star, or possibly a black hole. Nobody's entirely sure. The compact object is feeding. It's stealing matter from its companion star, pulling gas into an accretion disk that spirals inward at relativistic speeds, heating to millions of degrees, radiating X-rays and gamma rays, and occasionally, for reasons not completely understood, producing enormous radio flares. When Cygnus X3 flares, telescopes notice. These aren't subtle events. We're talking about radio emission that temporarily outshines nearly everything else in that frequency band across the entire sky. The system has a 4.8-hour orbital period, one of the shortest known for this type of binary, and that rapid orbit produces complex variability in its emission as the accretion disk gets periodically eclipsed and exposed. In mid-January 2026, Cygnus X3 produced a major radio flare. Multiple observatories detected it. The timing was noted, and then scientists moved on because Cygnus X3 flares relatively often. It's a known variable source. Cataloging another flare is like cataloging another sunrise. Interesting if you're studying that specific star system, routine for everyone else. Except for the timing. The flare overlapped with Earth's electromagnetic instability, the Schumann anomalies, the sustained geomagnetic storm, the seismic clustering, all happening at the same time that high-energy photons from a stellar explosion 24,000 years ago were washing over Earth's upper atmosphere. Now let's be very clear about what distance means here. 24,000 light years. That's the distance light travels in 24,000 years. That radio flare we detected in January didn't happen in January. It happened during the last ice age, when woolly mammoths still roamed, and humans were just beginning to develop agriculture. The light from that event has been traveling through space ever since, finally arriving at Earth in 2026. So there's no causation here. Cygnus X3 didn't know Earth was having electromagnetic problems and decided to flare. The flare happened in the deep past. The timing is coincidence. Or is it? This is where we have to think carefully about what coincidence means in a universe that's not actually random. Events can appear independent when you're looking at them locally, but be connected when you zoom out far enough. Phase relationships can exist across distances where direct causation seems impossible. Consider this thought experiment. Imagine two metronomes on a wooden plank. Set them ticking at slightly different rates. At first, they're out of sync. One ticks while the other talks. But leave them long enough, and the vibrations each one sends through the plank start to influence the other. Eventually, they synchronize. They lock into a phase relationship where they tick together. Not because either one is controlling the other, but because the coupling through the shared surface forced them into coherence. Now, scale that up. Way up. Instead of metronomes on a plank, imagine oscillating systems embedded in a galaxy-scale medium. The interstellar medium isn't empty. It's filled with plasma, magnetic fields, cosmic rays, and electromagnetic waves at every frequency. That medium has structure. It has filaments and voids and regions of varying density. And it couples systems across enormous distances through mechanisms we're still working out. Could galactic-scale electromagnetic structures create phase relationships between star systems and planets separated by thousands of light years? Could there be large-scale field alignments that we don't detect locally because we're embedded in them, like fish unaware of the ocean? This is speculative to the point of being science fiction, but it's not impossible physics. We know the galaxy has a large-scale magnetic field. We know plasma can support wave modes that travel at speeds below light, but still cross interstellar distances. We know that coherent structures exist in the interstellar medium that span hundreds of light years. What we don't know is whether those structures can create correlations between events in different star systems. Whether the flare timing from Cygnus X3 and Earth's electromagnetic disturbances could both be responses to some larger galactic field reconfiguration that we're not equipped to observe. The alternative is pure coincidence. And coincidence is fine. Unlikely things happen. With enough objects doing enough things across enough time, you'll eventually see apparent patterns that mean nothing. But here's where the probability argument gets uncomfortable. If this were just the Cygnus X3 flare and one anomaly on Earth, coincidence is easy to accept. But it's not one anomaly. It's the solar wind behavior, the seismic clustering, the Schumann disturbances, the timing overlap with an upcoming planetary alignment. Each individual correlation is weak. Each one can be dismissed. But when you stack them all together, when you calculate the probability of all these independent, low-probability events occurring in the same narrow time window, the numbers start to get uncomfortable. Statisticians call this the prosecutor's fallacy when it's done wrong, but it's not fallacious to notice that many unlikely things happening simultaneously requires explanation. Either you're experiencing a rare coincidence, which happens but is by definition rare, or there's a common cause you haven't identified. And here's where phase coherence comes back into play. Phase coherence doesn't require instantaneous communication or faster than light effects. It just requires that separate systems are responding to the same underlying field or wave pattern. If there were a large-scale electromagnetic structure in our region of the galaxy, something oscillating at a very low frequency, something with a wavelength measured in light years, then different systems could appear to coordinate their behavior while actually just responding independently to the same driver. Earth would see changes in near-space electromagnetic conditions. The Sun would experience perturbations to its magnetic field that alter solar wind characteristics. Seismic systems would couple to electromagnetic changes. Cygnus X3's accretion disk would experience instabilities that trigger flares, none of them talking to each other, all of them marching to the same galactic drumbeat. This is the kind of hypothesis that's almost impossible to test with current instruments. You'd need simultaneous monitoring of electromagnetic fields across interstellar distances. You'd need baselines measured in light years. You'd need to be able to separate local effects from galaxy-wide patterns. We can barely do this in the solar system, let alone across the galaxy. But the hypothesis makes a prediction. If this kind of large-scale coherence exists, it should show up in timing correlations across many systems, not just Earth and Cygnus X3. And that's where things get interesting. Because when you start correlating solar activity with stellar flares and planetary electromagnetic behavior across the solar system, patterns do emerge. Weak patterns, noisy patterns, patterns that could absolutely be coincidence or selection bias. But they're there. Space isn't empty, and it isn't random. It's structured, and structures can support waves, and waves can synchronize oscillators, and oscillators can coordinate behavior across distances where no human would think to look for connections. January's coincidence might not be coincidence at all. It might be Earth, moving through a medium we don't fully understand, responding to signals we don't normally detect, while simultaneously being observed by signals from stellar systems that are themselves embedded in the same medium, all of it pulsing in a rhythm set by galactic-scale physics. But Earth isn't just sitting still, waiting to be hit by signals. Earth is moving. We're orbiting the Sun at 18.5 miles per second. The Sun is orbiting the galactic center at roughly 140 miles per second. And that motion means we're constantly passing through different regions of space with different properties. What if, in January and February 2026, Earth's path is carrying us through something we've never encountered before? October 19th, 2017. Astronomers detect an object moving through the inner solar system on a trajectory that doesn't belong. It's moving too fast, at an angle too steep to the plane of planetary orbits. Orbital calculations confirm what shouldn't be possible. The object isn't from our solar system. It came from interstellar space. They name it Oumuamua, Hawaiian for scout or messenger. It's the first confirmed interstellar visitor in recorded history. It's small, maybe a few hundred meters long, shaped like a cigar or possibly a pancake. Nobody's quite sure because it's already leaving by the time we spot it. It behaves strangely, accelerating slightly without any visible comet activity, defying easy explanation. And then it's gone, climbing out of the solar system, never to return. 2 years later, in 2019, amateur astronomer Gennady Borisov spots another one. This time it's clearly a comet, a dirty snowball with a visible tail. Orbital analysis confirms interstellar origin. Scientists name it 2I/Borisov. The fact that we've now detected 2 interstellar objects in 2 years forces a recalculation of how common these visitors might be. The new estimates are startling. There might be thousands of interstellar objects passing through the solar system at any given time, possibly tens of thousands. We just can't see most of them because they're small and dark and moving fast. Detecting them requires luck, good timing, and telescopes scanning the right patch of sky. Which brings us to 3I/Atlas, potentially the third confirmed interstellar visitor. I'm qualifying this because the observational status is still being finalized. Orbital uncertainties are significant, and confirmation of interstellar origin requires multiple observations over time. But preliminary analysis suggests this object is not bound to the Sun. Its trajectory is hyperbolic. It came from outside, and it's heading back outside. Right now, in late January 2026, 3I/Atlas is moving through the inner solar system on a path that will carry it near Jupiter's orbit in the coming weeks. And right now, Earth's orbit is intersecting the region of space that 3I/Atlas has already passed through. Why does that matter? Because interstellar objects don't travel alone. They're embedded in their own local environment, carrying with them traces of wherever they came from. If 3I/Atlas is a comet, and current observations suggest it might be, then it's actively sublimating, turning ice into gas and releasing dust as solar radiation heats it. That creates a coma, a cloud of gas and dust surrounding the nucleus, and a tail that can extend for millions of miles behind the object. But there's something else that comets, especially interstellar comets, might carry. Plasma, ionized gas with embedded magnetic fields. As the comet nucleus releases material, that material gets ionized by solar ultraviolet radiation and solar wind impacts. The ionized gas forms its own plasma environment, distinct from the solar wind, with its own magnetic field structure. And here's where it gets interesting. When Earth passes through the debris field left behind by a comet, we typically see meteor showers. Dust particles hit the atmosphere and burn up, creating shooting stars. That's a well-understood phenomenon. We can predict meteor showers years in advance based on Earth's orbital intersections with known comet trails. But what about passing through a plasma cloud? What about encountering regions of space where the electromagnetic field structure is different from normal because a comet has recently modified it? We don't have good empirical data on this because we've never confirmed doing it with an interstellar object before. Oumuamua was already leaving when we spotted it. 2I/Borisov passed through the solar system at a distance from Earth's orbit that precluded direct interaction. 3I/Atlas, if the trajectory calculations hold, might be the first interstellar visitor where Earth crosses its path close enough in time to encounter residual effects. Those effects would be subtle, not catastrophic, not even obviously detectable without looking specifically for them. Satellite drag anomalies as Earth moves through slightly denser plasma. Ionospheric noise as irregularities in the background, electromagnetic field propagate downward. Slight changes in the coupling efficiency between solar wind and magnetosphere as magnetic field orientations shift. The kind of effects that would show up as weak signals in multiple datasets. The kind of effects that would be easy to dismiss individually, but harder to explain collectively. The kind of effects that might prime Earth's electromagnetic systems to respond more strongly to solar wind inputs than they normally would. This is deeply speculative. Confirming it would require precise measurements of plasma density and magnetic field orientation in near-Earth space, correlated with the known position of 3I/Atlas in the weeks before and after Earth crosses its path. That data might exist in satellite archives. It might not. Space weather monitoring focuses on solar inputs, not on local variations that could come from other sources. But consider the hypothesis seriously for a moment. Earth, in January 2026, is moving through a region of space that has been modified by an interstellar visitor. That modification isn't dramatic enough to be obvious, but it's sufficient to alter the electromagnetic baseline of near-Earth space. When solar wind arrives during this period, it couples more efficiently or differently than normal. The magnetosphere responds unusually. The ionosphere gets disturbed. The global electric circuit picks up noise. Schumann resonances start showing complex behavior. And all of this is happening while Earth is also experiencing unusual seismic activity. Not because the plasma is causing earthquakes directly, but because the electromagnetic changes are subtly modulating the threshold conditions in ways we don't fully understand yet. Then add the planetary alignment. Add the fact that on February 20th, Saturn and Neptune reach conjunction while multiple other planets arrange themselves in geometric configurations that maximize gravitational and electromagnetic coherence across the solar system. The alignment itself doesn't generate enormous forces, but the alignment represents a moment of maximum coupling efficiency between planetary magnetic fields and the interplanetary medium. If that medium is already modified by 3I/Atlas plasma, if Earth's systems are already primed by weeks of unusual conditions, then the alignment becomes a focusing lens rather than a source. This is the interstellar wildcard. The variable nobody's pricing into their models because it's too new, too uncertain, too outside the normal framework of space weather forecasting. We're still learning what it means to have interstellar objects passing through our neighborhood. We're still working out whether they leave traces that matter to Earth. And we're doing this learning in real time, with limited data, while the system evolves around us. February 20th might mark the moment when Earth exits the modified region, when the plasma cloud from 3I/Atlas has dispersed or shifted enough that conditions return to normal. Or it might mark the moment when all the subtle perturbations reach maximum alignment, creating a brief window where the coupling between all these systems peaks before decaying back to baseline. Either way, Earth isn't a static target sitting in empty space. We're moving objects passing through a dynamic medium, and that medium can change in ways we're only beginning to detect. The biggest assumption error we can make is thinking that space is the same everywhere all the time, that the electromagnetic environment Earth experienced last year is the same one we're experiencing now. Because if it's not, if something has changed in the local structure of the interplanetary medium, then all our models, all our predictions, all our expectations based on historical data might be calibrated to the wrong baseline. And that brings us to the final piece of this puzzle. The recognition that maybe the limitation isn't in the cosmos. Maybe the limitation is in us. In our ability to detect patterns that don't fit our categories. In our models that assume stability when stability isn't guaranteed. Maybe what's really changing in February isn't the universe. Maybe it's our capacity to see what was always there. Earthquakes don't announce themselves clearly. They leave hints. Tiny stress changes. Subtle electromagnetic signals. Patterns in foreshock activity. But those patterns are buried in noise. Thousands of micro-earthquakes happen every day. Electromagnetic sensors pick up interference from power lines and thunderstorms and human activity. Separating signal from noise requires processing vast amounts of data and knowing what to look for. Humans aren't good at this. Not because we're stupid, but because our brains evolved to detect threats on savanna timescales. We're excellent at spotting predators in grass, We're terrible at detecting multidimensional correlations in seismic datasets spanning decades. So we built machines to do it for us. In the last 5 years, artificial intelligence has become a standard tool in seismology. Machine learning algorithms trained on historical earthquake data can now identify foreshock patterns that human analysts miss. They can detect subtle changes in seismic wave velocities that precede ruptures. They're not perfect. They make false alarms. They miss events. But they're getting better. And crucially, they're finding things we didn't know to look for. The same thing is happening in space weather forecasting. Traditional models of geomagnetic storms rely on physics-based simulations. You input solar wind measurements, run the equations, predict how Earth's magnetosphere will respond. These models work well for typical conditions. They struggle during extreme events, or when the coupling mechanisms behave unusually. AI approaches this differently. Instead of encoding physical laws explicitly, machine learning systems learn patterns from data. Feed them decades of solar wind measurements and magnetosphere responses, and they start recognizing correlations that the physics-based models miss. Subtle timing relationships, multi-frequency coupling, non-linear feedback loops, and critically, AI systems don't get anchored by what's supposed to happen. If the BZ component is positive, but the geomagnetic storm is intense anyway, a physics-based model will struggle to explain it. An AI system will just note the correlation and look for other times the same pattern appeared. This is both powerful and dangerous. Powerful because it can detect genuine new phenomena. Dangerous because it can also detect statistical flukes that look like patterns but aren't. The key is having enough data and enough validation to tell the difference. Which brings us to January 2026 and the question of what AI systems are seeing in the data. Several research groups now run AI-based monitoring systems for earthquake forecasting, space weather prediction, and atmospheric electromagnetic activity. These systems aren't public. They're research tools, experimental, not ready for operational use. But they're collecting data and flagging anomalies in real time. In January, multiple AI systems flagged unusual patterns, not in one domain, but across domains. Seismic forecasting algorithms noted the clustering of magnitude 5 events and the absence of larger triggers. Space weather AIs highlighted the sustained positive BZ geomagnetic coupling as outside normal parameter ranges. Schumann resonance analysis systems mark the 72-hour disturbance as a multi-sigma outlier. Each flag individually is interesting, but not alarming. AI systems flag anomalies constantly. Most turn out to be instrumental artifacts or normal variation that happens to look unusual. But when multiple independent AI systems in different scientific domains all flag the same time window, that's when human researchers start paying attention. Because here's what AI is good at that humans struggle with. Multi-domain correlation, finding patterns that cross disciplinary boundaries. If seismic activity and electromagnetic disturbances are connected, a seismologist might not notice because they're focused on earthquake data. An atmospheric physicist might not notice because they're focused on ionospheric measurements. But an AI system that's been given both datasets can spot the correlation immediately. And that's what appears to be happening. AI systems with access to integrated Earth observation data, solar wind measurements, seismic networks, and electromagnetic monitoring are finding correlations that individual research groups wouldn't detect. Not because those groups aren't smart, but because they're specialized. They're looking at their piece of the system, not the whole system simultaneously. The challenge is interpreting what the AI is finding. Machine learning systems are notoriously bad at explaining themselves. They can tell you that pattern A correlates with outcome B. They can't always tell you why. They found the relationship in the training data through statistical optimization, not through physical understanding. So, when an AI flags January 2026 As anomalous across multiple domains, researchers face a dilemma. Do we trust the machine? Do we assume it's found something real? Or do we demand physical mechanisms and causal explanations before taking it seriously? This is where we run into the limits of human detection, not in our instruments, but in our epistemology. Science traditionally demands mechanism. Observation is important, but understanding is paramount. We don't accept that X causes Y unless we can explain how the causation works. AI doesn't care about mechanism, it cares about prediction. If X correlates with Y reliably enough, the AI will use that correlation whether or not we understand why it exists. And increasingly, AI systems are finding correlations that work but that we can't explain yet. This creates an uncomfortable situation. We have machines telling us that something unusual is happening. We have data supporting that claim, but we don't have complete physical models explaining why the data looks the way it does. Do we act on incomplete understanding? Do we wait for certainty? Do we accept that some patterns might be real, even if we can't fully explain them? February 20th, 2026 becomes a test case for exactly this question. The planetary alignment is predictable. The orbital mechanics are certain. What's uncertain is whether anything happens beyond the obvious gravitational and electromagnetic effects we can calculate. If AI systems are correct, if there are subtle multi-domain correlations building towards some kind of threshold event, then February 20th should show measurable changes in Earth's electromagnetic behavior, seismic patterns, or atmospheric conditions. Changes that wouldn't be catastrophic, but would be detectable. Changes that would confirm the machines were seeing something real. If nothing happens, if February 20th passes without any unusual activity, then the AI flags were false alarms. The correlations were coincidence. The patterns were noise. And we learn to calibrate our trust in machine learning systems accordingly. Either outcome is valuable scientifically. Either outcome teaches us something about the limits of our detection capabilities and the reliability of our tools. But there's a third possibility that's more unsettling. What if something does happen, but it's too subtle for our current instruments to catch definitively? What if Earth's electromagnetic systems shift baselines in ways that only become clear weeks or months later when you compare before and after datasets? What if the event is real, but distributed across timescales and spatial scales that make it hard to isolate as a discrete occurrence? This is where AI might be seeing things we can't. Not because the machines are smarter, but because they're patient. They can sit there correlating millions of data points across years of observations, waiting for patterns to emerge that would take human researchers lifetimes to notice. And what AI seems to be telling us, with varying degrees of confidence across different systems, is that something is different about January and February 2026. That the baseline has shifted. That Earth's coupled electromagnetic and geophysical systems are in an unusual state compared to historical norms. Whether that state persists or resolves on February 20th is the question. Whether the planetary alignment acts as a release valve, allowing perturbed systems to return to equilibrium, or as an amplifier, pushing unusual conditions to a peak before they decay. The meta-reveal here is that the cosmic event might not be cosmic at all. It might be cognitive. The shift might not be in Earth's systems, but in our ability to detect what Earth's systems are doing. We're living through the first moment in history, where AI can watch the entire planet simultaneously, correlating datasets that humans never had the bandwidth to cross-reference. We're detecting things that were always happening, but that we were too slow, too specialized, too limited by our wetware processing to notice. The dominoes were always falling. We just couldn't see the whole chain until we built machines that could. February 20th doesn't predict a catastrophe. It predicts a data point, a moment when multiple systems that have been drifting into unusual configurations either resolve back to normal or push through to something new. And critically, a moment when our AI monitoring systems will be watching everything simultaneously, collecting the kind of comprehensive data set that will let us test whether these cross-domain correlations are real or illusory. That's the experiment. That's the value of this alignment beyond its aesthetic appeal. It gives us a scheduled event, a known point of maximum geometric configuration that we can use as a temporal marker, before and after, changed or unchanged, signal or noise. And if it turns out the signal is real, if AI systems are correctly identifying patterns in Earth's behavior that precede this alignment, then we'll have learned something profound about the planet we live on. Not that it's fragile or endangered or about to transform, but that it's more dynamic and interconnected than we previously understood. The cosmic domino effect isn't ending. It's just becoming visible. And the most dangerous assumption we can make is that the system must behave the way it always has, when maybe, just maybe, it never behaved that way at all. We were just too blind to see the pattern until now.